Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay, today I will present the Engineering Fluid Mechanics Labs, which is the experiment title is Flow over Immersed Bodies and Boundary Layers. So we are from Group 3 and the session is 03. So this is our group members and my name is Muhammad Alifai Kabir Rosmani. My metric number is MA19187. Okay, for the background, Ludwig Pareto was the first to propose the theory that explains boundary layer effects in the early 1900s. The general fluid equations have been around for a while, but their solutions could not adequately capture flow effects like wing stalls. Brent was the first to notice that from a layer very close to the surface to a region far from it, the relative strength of the inertial and viscous forces altered. So for the introduction, a boundary layer is a thin layer of a moving gas or liquid that comes into contact with a surface like an aeroplane wing or the inside of a pipe. A continuum of velocities from maximum to zero develop around the boundary layer as a result of shearing force acting on the fluid in the boundary layer's fluid contact with the surface. Laminar flow occurs at the leading or upstream end of this boundary layers, whereas turbulent flow occurs at the trailing or downstream end. Two distinct boundary layers theory, which is laminar and turbulent. The external flow is the flow of fluids over submerged body or fluids flowing over submerged bodies. When an object is surrounded by fluid, external flows also refers to a lift and drag are produced. Both theoretical using analytic and computational techniques and the experimental approach are utilized to study the fluid force produced by external flows. So for the for the objective, first is to plot streamlines over the cylinder, orifice, and wind profile to identify flow condition. Next is to determine the speed distribution for a flat plate and to determine the boundary layer thickness of a plate surface subjected to longitudinal flow for smooth and rough surface. So that's all from me. Thank you.
Hi, Assalamualaikum. My name is Dr. Japtik Marvin. I will talk about the theory for the boundaries layer. Okay, boundary layer theory. Ludwig Prandtl is credited with developing the boundary layer theory with his paper on the motions of a fluid with very low viscosity, which was presented at the Third International Congress of Mathematicians in Heidelberg in August 1904, and later appeared in Congress proceeding the following years. This paper opened the door to understanding the motions of actual fluids, ushering in a new era in the study of fluid mechanics. However, the boundary layer theory inception stood in sublime isolation, which is nothing comparable had ever been proposed before, and publications on the topic ceased for nearly 2 decades, except for a few papers due to Prandtl's student. For the boundary layer concept, many technical applications involve the flow of fluid with very high Reynolds number and low viscosity value. The no-slips condition is not satisfied by this limiting solution, which means that the speed at the wall are not zero but rather finite. To satisfy the no-slip condition, the viscosity must be taken into consideration. This handles the transition in velocity from the finite value to the limiting solution near the walls to the value of zero directly at the wall. When Reynolds numbers are high, this transition occurs in a thin layer near the walls that Ludwig Prandtl refers as the boundary layer or frictional layer. As will be demonstrated, the boundary layer becomes thinner as the Reynolds number increases or as the viscosity decreases. Laminar or turbulent flow, one of the two different flow types mentioned in, can be occur within the boundaries layer. Then, one uses terms like turbulence boundary layer or laminar boundaries layer, which are both short for laminar boundaries layer.
Hi, hello, and good day to everyone. My name is Arvindan son of Tyagarajan, and my metric number is MA19143. Today, I'm going to present about the methodology for our boundary layer experiment. First, we are going to see about the apparatus that we use for our experiment. We use HM225.02 boundary layer apparatus. This is the image of our apparatus we use in our lab. In this apparatus, we have 12 elements. First we're gonna see about the laboratory trolley. This is the laboratory trolley, and then switch box for the flow the current, and the bench top. Normally bench is up, and then manometer panel. This is the manometer panel, and the fifth is the flow straightener, and sixth is the nozzle. Seven is a receptacle for the accessory module, and the eight is a thermometer. We have to use the thermometer, and then is a regulator flap, feed pipe, and outlet with the hood. And the final part is a radial fan. The next is we're going to see about the procedure. Procedure, first we have to measure the ambient temperature and the air pressure to determine the current air density. Because we have to do this. Why we have to do this? Because we have to use the current density to precise our final answer. If we forget to do this, our answer will be slightly different. Next is we have to place the plate at the x equals to 0 mm and lock it with the screw. We use two types of plate. One is a rough surface plate, another one is a smooth surface plate. We have both. We have to use this method. Next is from the manometer, we have to obtain the reference pressure variable. After that, we have to adjust the wind channel so that it will blow at the appropriate rate. We must set the precision regulator by 7 to 8. Next is the read of the initial measurement number of for pressure dynamic as we move the pickup tube up close to the plate. This number corresponds to the height of the y equals to 0.3 mm because the tube having a diameter of 0.5 mm. Next is the additional measured values are recorded up to the height of 1.5 mm at every 0.5 mm. And next is it was sufficient to record up to 5 mm of measured every 1 mm. Finally, it was the necessary to carry out these steps again for the other positions such as x equals to 20, 40, 60, 80, 100, 120, and 140. Next, we're going to see about the formulas that we use in our experiment. First, we use the formula to get the Reynolds number. We use this formula to get the critical Reynolds number. Next, we use this formula to get the speed. And then we use this formula for the total pressure. That's it from my side. My friend will be continued. Thank you.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Alifai Kabir Rosmani and my metric number is MA19197. Okay, thank you for my previous friend for the presentation. I will continue my presentation of the experiment with the results. Okay, from the graph, if we can see that if the boundary layer thickness increase, then the height recorded will decrease. This is due to the increase in the boundary layer thickness that will cause the pressure in the fluid flows from the pitot tube to manometer become higher, and this will further push the fluid in the manometer, thus lowering the height in the manometer. Okay, so next for the velocity. Based on the graph, we can see you can see the boundary layer thickness. If the boundary layer thickness increase, then the velocity of the fluid increase as well by comparing from the aspect of difference in distance of the plate or length of the plate exposed. The smaller distance produce a lower velocity. Uh, when the length of when the length of the plate is short, the boundary layer will become thin. Hence, the velocity will be lower. The thickness of the boundary layer increase with the length of the plate, where the fluid flows when the fluid flows by. Okay, next for the Reynolds number, uh, from the graph, the thickness, the thicker the boundary layer, and the Reynolds number increase due to increase in velocity. From the equation, uh, the Reynolds number increase due to increase in velocity from the equation. Hence, there are flows in the lamina and transition region. Reading the data according to the thickness of boundary layer, we can only observe a slight difference in the Reynolds number with the increased boundary layer thickness.
Assalamualaikum and hi. So my name is Muhammad Faizrin Aiman Bihaslin, ID number MA19144, and I'm going to explain about experiment 2.1 boundary layer for discussion part. So first, explain about the boundary layer thickness in the boundary surfaces. So the fluid layer close to a solid body move at the same rate as the solid. As a result, there are enormous velocity differences between the body and the free stream, resulting in higher shear stresses. As a result, viscous effect is predominant in this fluid zone, which is referred to a boundary layer, the thickness of fluid created if the fluid travels over each other like a pack of cards. It is called lamina. So for second discussion, what is the distance in the plate before the flow become the turbulent? What phenomena could be the reason of these changes? So the distance in the plate before the flow become turbulent, and the reason of these changes when the rate of momentum transfer between the surface and the free stream increases in a manner analogous to an increase in viscosity. The turbulence increases. It has three immediate effects such as the boundary layers form faster, the velocity profile thickens, and skin friction rises. So there's three total. So for the third discussions, what are the differences in terms of result for smooth and rough surface? The differences in terms of result for smooth and rough surface because the surface roughness height is less than the thickness of the lamina sublayer of the surface. There will be less turbulent and has a smoother surface. Moreover, it is because the surface roughness height is more than the thickness of the lamina sublayer. So the turbulent level begin to rise for the rough surface. So that's all from me for discussion. Thank you.
In conclusion, it is discovered that different aerofoil angles produce different lift and drag forces. Because different applications require different lift and drag forces, we are unable to provide the best solution. Additionally, we draw the conclusion from the experiment that surface roughness will influence the boundary layer and the Reynolds number. A rougher surface will result in a thicker boundary layer and a lower Reynolds number. This is because the viscosity effect has become significant and there is increased shear stress on the rough surface. The boundary layer will become thicker and the fluid flow velocity will decrease as these factors become more prevalent. Reynolds number will decrease as fluid flow velocity decreases because it is inversely proportional to the flow velocity. That's all from me. Thank you.